We want to see how to get the electric field at a point in space when you have many charges. We got already how to get the electric field due to a single charge. But now, what if you put many charges, many point charges in space? How would we then get the effect of those charges at that point P? We want to get an expression for it. So we know from before that if you put a test charge Q at point P, and you get the force on charge Q due to charge Q1 only, that it's given by this expression. So here the force on Q due to Q1 only is KE Q1Q over the distance squared between them times a unit vector that points from Q1 to point P. We know this. We also know that the force on Q due to charge Q2 is this vector. The force on charge Q due to charge 3 is this vector. And we know also that the total force on charge Q is just the sum of those forces that we got for each charge on charge Q individually. And this is the principle of superposition that we discussed before, and we discussed this in detail before. So we know all this. We can then put in the expressions for F1, the force due to 1 and due to 2 and due to 3, and we get this total expression for the force on Q due to all the other charges. Now, what do you notice is common between all these expressions? Of course, except for the KE. We know that KE is common, but what else is common? See here that the charge Q exists in all these terms because we're getting the force on charge Q. So what can we do with all these Q's? Why don't we take them out as a common factor? So we get Q multiplied by this big bracket. Okay, now from the definition of the electric field, what is the definition of the electric field at point P? Do you remember what that was? Can you state it exactly? The definition of the electric field, it said, get the total force on the test charge and divide by the test charge. If you do that, that Q that we had over here, when you divide by it, this is what's left over. And that then represents the electric field at point P due to all these charges. If you look at each one of those terms, it turns out that this expression is the electric field at point P due to charge Q1 only, as if all the other charges didn't exist. Because you see what it is, it's KE Q1 over the distance between charge 1 and point P times a unit vector from charge 1 to point P. So this is the electric field at point P due to charge 1 only, as if all the other charges didn't exist. And this is the electric field at point P due to charge 2, as if all the other charges didn't exist. And this is the electric field at point P due to charge 3, as if all the other charges didn't exist. So we can write this as EQP, Q1P, EQ2P, EQ3P, and so on. So you can see here that we can write the total electric field at point P as the sum of what? Write the total electric field at point P as the sum of the electric fields at point P due to each individual charge on its own. And this is basically the superposition principle for electric fields. So the superposition principle for electric fields comes directly from the superposition principle for the force.